y bienvenidos a esta conferencia del Instituto de Astronomía de la Universidad Galileo en una edición más de nuestras conferencias sobre astronomía y astrofísica. Esta es una conferencia fuera de serie. Vamos a hablar con una persona que es a nivel mundial reconocido como un PhD, un astrofísico, y nos va a hablar de un tema que está creando hasta cierto punto mucha plática, mucha polémica entre los cosmólogos. Se trata de el profesor Rajendra Gupta de la Universidad de Ottawa. El profesor Rajendra Gupta nos va a hablar hoy sobre su hipótesis de la observación de la edad del universo. Es decir, ¿es posible que el universo tenga una edad más grande que la que se ha calculado? Vamos a escuchar sus argumentos. La plática va a ser en inglés y esperamos que todos pongan mucha atención y nos den sus comentarios, ya sea durante la charla, porque así me dijo él, puede aceptarse preguntas en la charla, o al final. Así que esperamos. Voy a pasar ahora a presentar al profesor Rajendra Gupta. Professor Rajendra Gupta is PhD from the University of Allahabad, India. He is currently a professor at the University of Ottawa, who is teaching astrophysics and cosmology to senior undergraduates and graduate students. Professor Gupta enjoys teaching and learning through teaching. He has written over 100 research papers, primarily published in well-known refereed periodicals. His current research interest is in astrophysics, cosmology, and general relativity, especially the dynamics of the universe under evolutionary physics constants beyond the standard model. He has the hypothesis that the observed redshifts of distant galaxies are not only due to the expansion of the universe, but also caused by the photons losing energy due to cosmic drag while traveling over large distances. Professor Gupta, welcome to University Galileo in Guatemala. It's an honor to have you here, and I let you in the use of the word. Please go ahead in your presentation.
Thank you very much. I very much appreciate your invitation to give for me to give a lecture on some of the work I have been doing lately, and especially on my last paper recently published, in fact, in July 7th in the monthly notices of the Royal Astronomical Society, which has created somewhat of a stir in the astronomical community. And the reason for this is that in this paper, I have shown, among other things, that the universe age might be higher than the standard model predicts, which is instead of 13.8 gigayears, it could be 26.7 gigayears. And that is what caught the attention of people. It's just like any other paper, and it could have gone totally unnoticed except for this kind of claim, people might say, but it is yet to be proven in various ways. I have proven it only by few methods, and I'm going to show those what I have done. And let's proceed with that, with your permission.
Yes, thank you.
Thank you. Okay, the outline is I will talk about the James Webb Space Telescope cosmic dawn observations. That means very early when the time of reionization of the universe in what it has seen, the so-called impossible early galaxies. And that is causing some kind of problem, that they are not able to explain it with the standard models, or they have to stretch those models significantly in order to explain them. Then I will talk about how the resolving with lambda CDM Can it be resolved with lambda CDM? That requires unrealistic galaxy formation models. Resolving with twilight, if you try to use the twilight, and I'll talk about what twilight is a little bit later, then there are other problems with other observations it cannot comply with. And resolving with the so-called covariant coupling constant model, which I have developed, independently, it doesn't give very satisfactory results. However, when we combine the models, like the standard lambda CDM model plus the twilight and the covariant coupling constant model plus the twilight, then what we see that the results do become satisfactory, at least for the case of the what we might call CCC plus TL, covariant coupling constant plus TL. And that it satisfactorily fits the so-called the Supernova 1A data, the Pantheon data set, which is very important test for any model to pass from preliminary stage to the next stage. How about then, does it model fit the CMB bow? CMB is cosmic microwave background, bow is baryonic acoustic oscillation, BBN is Big Bang nucleosynthesis, globular cluster, and etc. data. We will talk about that. So let's see, what is the cosmology with James Webb Telescope says? Originally, Hubble telescope, which was launched in 1990, it has a diameter of 2.4 meters, optical to infrared range. It was receiving that and analyzing the data or spectra, light spectrum in that range, and it was in the Earth's orbit, or it is still in the Earth's orbit. Then the James Webb Space Telescope was launched on 25th of December 2021, diameter 6.5 meter, that means area is almost 10 times. Then it has capability to go from infrared to far infrared analysis, and it is in the L2, Lagrange 2 sun's orbit. Now, I should mention that Hubble telescope established, before the Hubble telescope was launched, there was a lot of debate about the age of the universe. It was from 7 to 20 giga-years, and they were not very sure about it. But Hubble telescope provided a lot of data, which pinned it down to about 13.8, based on the information it provided. Now, JWST, James Webb Telescope, is challenging to some extent that age, same way as Hubble had challenged the original one, and we have to see why it is challenging it, why there is a problem with that age. We will discuss about that. Let's see how far back the two telescopes can see. If this is the expanding universe, then HST can see back to about 1 giga-year from the Big Bang. So that's quite deep, but not quite in the reionization era. Whereas the James Webb Space Telescope can penetrate very, very deep, down to about 0.3 billion years, or 300 million years from the Big Bang. So that's the advantage. So it can see the galaxies and stars and all that. That was the object of it. And they were expecting that the galaxies and stars in that region, when Hubble and James Webb Telescope will see, will be very immature or very elementary type. But it didn't happen. And that is the big puzzle which we have been trying to solve, why it is so. Now, the quality of James Webb compared to Hubble. Here you can see this is called the ionic pillars of creation. The quality of image by Hubble and quality of image by James Webb. As I said, the age Hubble determined is 13.8 gigayear. James Webb, we don't know what it is. Dark energy expansion is speeding up. That was established by Hubble. Black hole in the core of most galaxies. That was established by Hubble. And how planets form and many other things. Now, in the case of James Webb, galaxies are very young, supposed to be very young. That means they can see galaxies in the range of up to about 15, Z equal to 15. That means better than 5 billion years, as I have shown in the previous one. But they appears to be highly evolved. That's the big challenge. And then it is trying to see exoplanets and many other things. Now, in summary, JWST observations are excessively large number of galaxies at very high redshifts in the range of 15. That is, the universe age at that point was only about 3 gigayears, which is not foreseen by the standard cosmological model. That is the lambda CDM model. Galaxies at these redshifts have disks, bulges, which indicate that they have passed through a long period of evolution. Spectroscopically, these galaxies resemble their counterparts in the local universe. Smaller galaxies are more massive than larger ones, which is quite the opposite of the common view on this. Now let us see some of these impossible early galaxies. These are the images from NASA and the European Space Agency, which shows the images of 6 candidates of massive galaxies. They are seen 500 to 800 million years after the Big Bang. The one of the bottom left, this one, contain as many stars as our present-day Milky Way, but is 30 times more compact. Why? How can it be so compact? There's another one, impossible early galaxy, which is called Mazy Galaxy. This one has spectroscopic observation revealed that this galaxy was detected 390 million years after the Big Bang. That makes it one of the 4 earliest confirmed galaxies ever observed. This is another one, which is called Glass Z12 Galaxy. This is at Z12 12.117, and that means even earlier than the previous one. There's a 350 million years after the Big Bang. And its mass is 10 to the power 9 solar masses, which is massive galaxy, and size is 1 kiloparsec. As per the lambda CDM model. See, size, when you say 1 kiloparsec, you don't measure their size in kiloparsec, you measure them in terms of the angular diameter. And that is then converted based on the model into the size. So when you use lambda CDM model, its size comes to kpc, 1 kilopascal. When you use the CCC plus TL model, which I have proposed, that comes to 10 kiloparsec, which is very reasonable. That is would be a galaxy of the reasonable size for that mass. Now, the angular diameter of a 10 kiloparsec size object as expected to be seen at different redshifts is shown in here. And this is from a paper from Nikita Lovyagin in Galaxies. And this one, you see there's a lambda CDM model. You will expect the size of the galaxy to be much, much larger. Angular size will be, this is the angular size we are saying. angular size will be much, much larger than it is seen. And similarly, now the lambda CDM model gives this, but when you take the Twilight model, which was shown by this author, Levigan, then it appears to fit the observed data on these galaxies. These red ones are the James Webb Space Telescope observation. The black dots and all those, they are from the previous observation, JWST observations. And also the galaxy size. Galaxy size, if you take the Twilight model, then they are about 10 times larger than the lambda CDM model, because they are model dependent. Physical sizes are model dependent. Angular sizes are what you measure. But the Twilight conflicts the CMB observation. Twilight can't fit the supernova data well, and then it fails the Tolman surface brightness test, because in expanding universe, you lose the brightness due to the time dilation, but that's not detected in the observations. Then it comes automatically, one would think, why not have a hybrid model? That means it is a standard expansion model plus the Twilight model, which should be able to explain this. Now, whether it's a Twilight model or the expansion model, light is traveling the same distance. The proper distance covered is the same. That then constrains the model parameters, and it becomes somewhat easier to manage. You don't need too many independent parameters because of that constraint. Then what we found, if we use lambda CDM plus Twilight model, it doesn't fit the James Webb Space data, whereas CCT plus TL has excellent supernova data fit as well as very good James Webb Space Telescope data fit. However, it increases the age of the universe. It also provides a lot of extra time, about 10 times more time to create the galaxies than is possible with the simple lambda CDM model. And it fits the galactic angular diameter data well. Let's see, the supernova data, that's the critical data to fit for any model before you can go further. So here is the supernova 1A Pantheon data, and here are the various models, lambda CDM, the CCC model, and CCT plus TL, which is the hybrid model, lambda CM and TL model. They all fit the data very, very well. Now, how about this one? Now, this is the data we had seen in the earlier slide. And here we have plotted the curves using various models. That is, now this is the lambda CDM model, which fits the low Z data pretty well, but not the high Z data. Then we go to the next one, the Twilight plus model. Plus means I have adjusted a parameter in there to improve the supernova fit in there. So that gives a very good fit. Next best fit to this appears to be due to the CCC plus TL model, which is covariant coupling constant per Twilight model. This one, and all the other models are still far away, like the lambda CDM plus TL model still doesn't fit the data well. And CCC model, covariant coupling constant, without the Twilight also doesn't fit the data well. And this has been published in this paper here. Now, very recently, after the publication of the last paper, we have done some more work and see how does it fits the CMB angular power spectrum. In fact, we haven't been completed that work yet. All what we have done is focused on the first peak in this CMB angular power spectrum and see whether we get the correct location for that. And it is at about the multiple moment of approximately 220. That's what lambda CDM gets, and we get exactly the same with our model. I'm going to discuss the model a little bit later on. I thought first I should discuss the results. And theoretical part of the model I would discuss toward the end. But what we need in there, in order to fit this curves, you have to have some adjustable parameter. Adjustable parameter in here is the baryon density. Baryon density, what we obtain for fitting the curve is 5% of the critical density, which is same as the lambda CDM model obtains. It obtains baryon density about 5% of the critical density. So these things are very encouraging. That means this code is definitely doing something right. My graduate student is developing a code to fit the whole observed Planck spectrum, but that will take a little bit of time. Then this something is called BAO, baryon acoustic oscillation, the scale of baryonic acoustic oscillation. So this is determined by two-point correlation function, theta s, which is plotted here as a function of the separation s of 1,000,000 galaxies, 0.2. In this case, redshift is between 0.2 and 0.7. This is and the peak in this function turns out to be at a separation of 150 megapascal when reduced to 0 redshift. That's called the acoustic scale. And this provides an imprint of the oscillation in the baryon photon fluid that results in the CMB anisotropy. So essentially, this CMB scale, which we find here, that's what this anisotropy in here propagates to form the galaxies and all those, and that perturbations in there are the one which are reflected in this galaxy correlation function. So lambda CDM model and CC plus TL model, they both yield the same BAO value, which is approximately 150 megaparsec. So that is another very encouraging confirmation about the CCC plus TL model. Now there's another one which was discussed by some people, the deficiency of the model, that it is the age of the universe is sometimes determined by the age of the globular cluster. Globular clusters are the clusters of stars, of actually up to 1,000,000 stars, and they harbor stars which are very, very old. So astronomers feel that the age of the globular cluster, if that can be determined, then that will give an idea of the age of the universe. Of course, the globular cluster age cannot be higher than the age of the universe, but in some cases, it has found that the age is much higher. Actually, but for many stars or cluster, it was found at one time quite a bit higher than 13.8 giga-year. But then when 13.8 giga-year was determined as the age of the universe, then people found a way or ways or modified their models so that the age does not exceed significantly above that 13.8 gigayear. But most recently, the paper published, or it was just announced 2 days ago on archives, Cornell Archive, on this paper, that the age of the globular cluster, some of the globular cluster NGC 104, is between 19 and 20 gigayears. How could it be? This result is still need to be further confirmed, but I just tentatively, one could see that there are the age of the universe we have determined may not be in conflict with the globular cluster. Moreover, globular cluster age can definitely be not higher, but lower than the age of the universe. Then the BBN, Big Bang nucleosynthesis. This thing we had tried with the old CCC model, which we used to call variable physical constant model at that time. And we got very good and interesting results, but that is not valid for the new model we have developed. And this is why this work has to be still done and repeated. So we can ignore this altogether. Now let's see, what are the key takeaways from these models? Now, H0 parameter, which is the Hubble constant is about the same for all these models. Lambda CDM CCC, lambda CDM plus TL, CC plus, all give the same Hubble constant, except the TL, tired light alone, not modified tired light, but just the ordinary tired light model doesn't give that result. But this one is closer to the Planck's value, by the way, which is about 67. Anyway, we can ignore that at this time, but these ones are giving about the same value. And what is the expanding universe component of the Hubble constant? This is H sub x is really denotes the expanding universe component of this. Of course, for lambda CDM and CCC, which has no tired light component, all of it is indeed, all of H0 is the expanding. But for the case of when we have lambda CDM plus tired light and CCC plus TL, we have to see what is the component. But you can see these values are also very close. The expanding component in the two cases is about the same, and the tired light component is this, much smaller than expanding. So expanding part is still dominates, but tired light component does modify the age of the universe as well as the observational data significantly. And how good the fits are, as we have shown in the graphically, but also you can see the number, the chi-square number for all of these things is about the same. And of course, very bad for the tired light. Tired light doesn't fit the supernova data. The modified one, which we have added additional part of it, that's the one that does a good job. And age of the universe is 13.8 gigayears for lambda CDM, 13.7 for CCC, which are very close to each other, and 19.25 for lambda CDM plus TL. So you might say, yeah, it also increases the age of the universe quite significantly, but it doesn't fit the James Webb data of the impossible early galaxies. So in spite of the fact that it does increase the age significantly and allows sometimes to galaxies to evolve, it doesn't fit the size data. And because if you see the size, angular size, and we determine the physical size from angular size, it doesn't fit that data. Now, let's see. What is the universe age as a function of Z? We have plotted it from 1.1 to 1000 Z. up to the almost close to the reionization era, or CMB, I should say, cosmic microwave backgrounder. So age in gigayear, this is, we have determined the age of in gigayears here. This is the lambda CDM model, which gives you 13.8 gigayears. And the CCT is about the same. Then lambda CDM plus TL gives you somewhat higher age, and this one gives even higher age. And it's a log scale, so when you expand it, then you can see a real difference. But one of the things we see here is this is the age of the universe from the time of the Big Bang. That age difference increases dramatically as you go in the value of Z. So for example, if you are observing a Z equal to 10, then it will be significantly more than just twice the age. You can get about 10 times. I will show you in another one. This age ratio. Age ratio compared to the increasing value of Z. That means CC plus TL divided by the value at lambda CDM. I have used L for lambda here. And the LCDM plus TL, LCDM, this is the ratio we have tried to determine. So essentially you can see at Z equal to about 10 or 15, the lambda CDM plus TL gives you an age increase of about, this is 1, 2, 3, 4, about 4, whereas this one gives about 20. Oh, that is, sorry, at 10, and here it gives you, yeah, about 3 or 4. So there is significant increase in the age ratio. So if it was 300 million years for creating the galaxy at 10 using lambda CDM model, it will be 3 billion years. 300 million years versus 3 billion years, which will be for the creation of the galaxy at Z equal to 10. So there's a lot of difference in that. So 10 times more in this case. Now, the Twilight Redshift is a fraction of expanding universe redshift. What is the fraction of Twilight component? Twilight component of redshift versus this. That again is almost quite significant in here, in the range of about 15 to 20% in here, but it decreases significantly. From lambda CDL model, it decreases much more rapidly than for the other model, CCT plus TL. So this means the Twilight component is significant only at current epoch and not so much at the earlier epoch. Then actual size and object as compared to the observed size. Here again we see as compared to the lambda CDM, or we can times the lambda CDM. So lambda CDM is 1, and with all other models, how much it increases compared to 1. So you can see at about 10, here we have about 9 to 10 times increase using the CCC plus TL model. And this is, I brought this back again to show all these results which we discussed earlier. So the angular size here, what we have done, angular size is for 10 kiloparsec objects, because we don't know what is the actual size of those galaxies is. So we have assumed that we know the angular size, and we then convert them into the physical size of those objects. And we do the other way around we take the 10 kiloparsec object and see what their angular size would be at different Z values.
Professor, we have a question.
Yes, please.
The question is, why is it important that galaxies meet the angular size?
Because angular size is what is measured. What JWST is doing is measure angular size. And then using that angular size in the model in question, we infer the physical size. And physical size is important because then you say, okay, if I have so much mass of the galaxy and it appears highly evolved, why its size is so small? Physical size is so small, but physical size is a function of the model you use rather than actual size. Actual size is only angular size, what you measure. Does it answer your question?
Yes, thank you.
You're welcome. Now let's see, what is the twilight effect? The photon energy, they lose energy. Photon energy loss is proportional to photon energy itself and the distance traveled. That means d, h nu is proportional to h nu times the distance traveled, dr. Now, if we use this relation, nu equal to c over lambda and z definition of z and all that, and integrate this equation, then we get this thing. Now, if we compare this equation in the low z limit to the Hubble's law, which is this, then we get this equation, dp equal to c over h0 ln 1 plus z. But it fails to fit the Supernova 1A data. Tolman surface brightness test, it fails. Due to it doesn't have time dilation, so it appears to have brightness which is higher than observed, and then doesn't see the CMB observations, why it is so isotropic. Now, let's talk about the variable coupling constants. Dirac in 1937 predicted the variation of gravitational constant based on his large number hypothesis, and he derived that gravitational constant scales like the time of the universe, 1 over t. That gives g dot by g is equal to minus 1 over t. And if time is the age of the universe, approximately, then it is inverse, it is like h0. G varies as h0 here. And taking t to be 2 gigayears, g dot by g turned out to be minus 5, 10 to the power minus 10 years minus 1. Remember, at that time in 1937, the age of the universe was assumed to be about 2 gigayears, and it gives this number. Now, today, we have 14 gigayears, or 13.8 gigayears. The known age, we get approximately g dot by g, the variation of g, as 7 times 10 to the power minus 11 per year. Actually, this is approximately what we have determined using our CCC plus TL model. Now, Uzan in 2011 said, if one, and I have given this reference of Uzan here, if one constant varies, then other must also, and their variations correlated. So that means let's try to understand how the other constant might be. One of the problem in various observations, okay, I will discuss in a moment, I shouldn't jump ahead of at this point. Okay, so what is covariant coupling constant? We assume the coupling constant vary simultaneously, not only one constant vary, but multiple. Why? Local engine energy conservation leads to the gravitational energy should scale like the mass energy, rest mass energy, thermal energy, then the photon energy, and this is the electrostatic energy. All these should scale. If we relate their scaling, then we come with this kind of scaling relationship. Now, if we assume the mass electron charge, and alpha, which is the fine structure constant, are invariant. And then the R, the distance, is measured in units of speed of light. This relation can only be satisfied if G scales like C cube, scales like ABC, scales like HC, which leads to this relation essentially. Now remember, if we constrain one, we constrain all. That means variation of all can be represented by one-dimensional less function, which is we might call f alpha t. Now, if we don't say that the f alpha t, this equation doesn't tell f alpha t should vary. It might as well be a constant. But if any one of them vary, then all of them vary. So we can write something like this in terms of a single function determining the variation of various constants. And I will discuss a little bit more in a few minutes. On dimensional arguments, we can see it slightly differently. What is the dimension of G? This. C, this. Length, mass, time. C, length, mass, length, time. H, this, KB, and length, of course, is L. So that means G scales like L cubed, C scales like L, H scales like L squared, KB scales like L squared, and length scales, of course, like L. So this is the scaling law established just by analyzing the dimensions of this. So we might say, as the universe expands, it's not only expanding at a cosmological scale, but maybe it is extending or expanding, the length is also changing in some way. Dimensional length in these constant is also evolving. Now, how do these constants vary in the covariant constant model? I plotted that based on the CCT model, which we have analyzed in the published paper. These are shown here. At present value, it is 1, and these are the increase in the value in the past with increasing z, that these values increase. This is Hubble constant and Boltzmann constant. Here it is G, gravitational constant, and the speed of light. So this is the variation. And what we give, that we have assumed Fz, or which is scales like Ft scales like exp, alpha t minus t0. Alpha is not fine structure constant. This is a constant of defining the strength of the variation of these coupling constants. Now, what is the test of the variation of the constants? There's a lot of effort has been done in measuring the variation or constraining the variation of the gravitational constant, because that's what was predicted by Dirac. And this has been done by lunar laser ranging, solar system radar data, binary pulsars. They all depend essentially on Keplerian orbits of astronomical bodies that are precisely measured via the speed of light. An orbital period is given by this, p square equal to 4 pi square r cube g over m. And measurement of the variation of p leads to the measurement of the variation of g. However, if you see in this relation, you remember what we said, g scales like f cube, and r scales like f. So this scales like f cubed, this scales like f cubed, so their variation cancel. If you constrain, there's no variation here, only vary here, then automatically you will find that this is not varying. As I said, you have to allow the variation of all constant, because R is determined in the units of C. And C, we know how it scales with G, is C cubed, and G, which scales like C cubed. So they cancel. So they essentially say most stringent constraint on the variation of G. But they are not determining variation of G. They are determining the variation of G dot by G minus 3C dot by C, which is 0 in our case. Now, gravitational lensing has been used for constraining the variation of C, that is C dot by C, measuring C dot by C. However, gravitational lensing, without going into detail, is due to optical path length difference. So essentially, you have an image here gravitationally lensed, and depending on the path they are taking, the images formed could have different paths, and the variation of the luminosity, original quasar, the variation of the luminosity can be used to detect the delay in the images arrival time or from different images. And this could be in the range of 55 days in one case. And this could be due to the optical path length difference, which again scales like GM over CQ, and due to the Shapiro delay, which is gravitational time dilation differences, and that is again proportional to GM over CQ. So you see the G and CQ, these variations cancel each other. As a result, you will not observe any C variation using gravitational lensing because it's cancellation effect, not because C is not varying, but because the G variation and CQ variation cancel each other.
We have another question.
Yes, please.
With the power spectrum and the hybrid model CCC plus TL, are they able to obtain the spatial curvature of the universe, and does it fit with that observed with lambda CDM?
Actually, we have assumed in this study the flat universe. We have not put any curvature on this because most studies show the curvature is 0. So in our initial study, we have constrained our model to a flat universe.
Okay. Thank you, Professor.
Okay. Now, the gravitational waves can also constrain G dot by G, variation of G. But again, it involves factors that depend on G over C cube. But we have seen that G over C cube cancel each other. The variation of that, they cancel each other. So they will not detect any variation of G as a result of that. Then let's consider stellar evolution. How much more time I have, if I may ask?
Hey, you have 15 minutes.
15 minutes? Okay, thank you.
It's okay?
Yes, thank you.
Okay.
Stellar evolution and universe age. And as I mentioned, the globular cluster age or globular cluster stars in the globular cluster, the oldest star in the globular cluster, which are formed at the cosmic dawn, for example, they can give an idea of the age of the universe. So I don't have to go through this thing just to give graphically that the stars evolve with time depending on their masses, and the turn-off time at the main sequence would provide you about the idea or the age of a star. And that can then be used for knowing the the age of the cluster to which that belongs. But this is again are very much model dependent. So we have to be careful. And when we try to apply a new model, we have to make sure the way we apply is not just allow one of the constant to vary, but all of the constant which are in a model are allowed to vary. Now, the globular cluster contains very old star believed to be formed at cosmic dawn, extremely low metallicity. The age of the oldest star determines the cluster age, assuming all stars in the cluster are formed at the same time. Methuselah, in some other stars, ages are higher than 13.8 gigayears. And we have seen that a very recent archive preprint shows some of the cluster ages to be 19 to 20 gigayears. That means this age is not in conflict with the age 26.7 determined using the CCT plus TL model. Now, this is one thing I have discussed many times in the colloquia I give. The challenge, one of the challenges to design an experiment, cosmological or on Earth, which unequivocally confirms or falsifies the predicted variation of the coupling constants. In my paper, without going into detail, I have predicted what the variation should be, similar to that what Dirac predicted. The problem is designing an experiment in which the coupling constant variation do not cancel. Most they will cancel. And second, measurement accuracy is in the range of 1 times 10 to the power minus 10. So both things are not met. I have discussed with many people who do high precision experiments, but they have, like at NIST in the USA, the Standard Institute there, but nobody has come up with anything which can measure these experimentally. What is the CCC model? Just briefly, theoretically, this includes the distance measurement using speed of light in this FLRW matrix, which is Friedmann-Lemaitre, Roberts, Walkerson matrix, which is, we write, normally it is write ds square, c square, a square, and this. What we have added is ft square, and c is varying, so we added ft square, then r is varying, and r variation is determined by ft. We have added ft square here. So this is the new metric defined for the CCT model. Now, the Einstein equations, when we take them with lambda equals 0, and resulting Friedmann equations using this metric, not the other metric, then what we get, and we use this ft equal to this, then the equation, the new equations we get, Friedmann equations, is a dot by a plus alpha. Alpha is defining the variation of this, not the fine structure constant, remember, equal to 8 pi g or 3c squared epsilon minus ac squared by a squared. Remember, in the case of the standard model, alpha is not here, and we have lambda by 3 here, which is lambda is the cosmological constant divided by 3 here. That disappears here, and we have alpha coming in this configuration. Of course, we can bring alpha on that side too, separate it, and then we will find alpha minus 2 alpha plus alpha a dot by a. Now, minus alpha squared minus 2 a dot by a alpha, which will come here. That means lambda is replaced by those things here. And this is the second equation, and this is the continuity equation. Remember, in continuity equation, in the lambda CDM model, this is 0. So all these equations, if you put alpha equal to 0, that means there is no variation in the constant. We get back the standard equation without lambda, because we have already taken lambda equal to 0. Alpha equal to 0, we get back the same old equations. Now, assuming that the universe is flat, the proper distance for the CCC expansion universe will be given by this equation. And proper distance for retired light, we have already shown it is this. But the distance traveled by the light, whether it is due to expansion of the universe or due to retired light, is the same. So we can write dp equal to dpx equal to dpt. And since we know 1 plus z, the way redshift or expansion modify is multiplicative effect, and then from the very small redshift limit, by equating those, we can find these relations and solving numerically under this condition that dpx minus dpt must be equal to 0, yields a relation between zx and zt in terms of z. After we account for the energy loss due to redshift and time dilation, the distance modulus can be written in this form. And this is what then is used for fitting the data. Okay, so let's see what is the consequence. I think this might be my last but one slide. Just be patient for a few more minutes. What is the dark energy and dark matter? In the case of the lambda CDM model, we know we have dark energy, which is due to lambda. Dark matter is this, turns out to be through the CMB analysis and other consideration. And what we are left with the normal matter to be about 5%. Dark energy and dark matter together constitute 95%, and 5% is the normal matter. And is the dark energy is supposed to be causing the current accelerated expansion of the universe. So this is what is considered to be causing the expansion. Is the expansion of the universe an evidence of dark energy? You can frame the questions in different ways. But one of the problem is the energy of the universe is continuously increasing due to the expansion of the universe. Why? Because dark energy density is constant. Its density is constant. So if the density is constant and the volume is increasing, that means the energy content of that volume is increasing. So it means energy is not conserved. And as I had tried to say earlier, that in case of CCT model, we have this equation in a flat universe. And in case of lambda CDM, we have this. So this is the dark energy. In our case, we don't have dark energy. We can't call what is dark energy or dark matter. And in the case of lambda CDM, this is divided into the two energies. This would be this is the matter, dark matter, total matter energy. Sorry, total matter energy, and this here we have total energy density. We cannot divide into matter or dark matter, dark energy or dark matter, or regular matter and dark energy. So here, what we see, the 5% thing is still we get when we fit the data. We don't know what is, in this case, what is dark energy and dark matter. We only know the combined effect is that we have only 5% of the critical energy is the critical density is the normal matter or baryonic matter. Everything else we don't know what it is. So we can say in summary that this model, covariant coupling constant plus TL model, light model, resolves impossible early galactic problems. It is consistent with the CMB first peak and Bower data. It yields baryon density, the same as the lambda CDM model, that is 5% of the critical density. It is not in conflict with the globular cluster ages. And the constants variation predictions not in conflict with observations either. So this is what we have done, but here a lot more work has to be done to really prove that this model is legit or legitimate. The immediate future work which we want to do using this model is the full CMB spectrum fit, then BBN, Big Bang nucleosynthesis abundances calculation, and the globular cluster ages determination using this model. And I think one of the things I would say that we do have some financial support available to the people who might want to do research in this field. Thank you very much. That's about all what I wanted to talk. And now you can have open questions.
Thank you very much, Professor Gupta. It was a very high-level talk for us, but we appreciate your talk, and we have some questions here. Number one question is the CCC plus TL model only based on conjecture, or does it have solid evidence?
Actually, solid evidence, none of the model cosmological models have solid evidence. Nobody has any evidence for lambda, why lambda is there. So to say that do we have solid evidence, that means do have solid physics behind the variation and why they vary? Do we have the solid physics why the tired light phenomena happens? I would say no. That's another challenge people have. We only see that these kind of approaches or consideration fit the observed data very well. Whether it's lambda CDM model, whether it is our model, the same kind of limitations are still there.
Thank you, Professor. I have another question for you, which is more not so technical. It is more about, can you give us some words about what would be the consequences of if it is proven that the universe is older than we thought previously? Instead of 13.8, it has 27.6 giga years. What would be the consequences of that for our astronomy in general?
Actually, in general, most of the astronomy is not going to be affected with this kind of change. I would say almost most of the astrophysics, which is based on the observations of the nearby objects, which is very low Z redshift, they will not be affected. But what will be affected is how the galaxies and star forms in the early universe. Those will be affected, and they will then affect the model, which is the dark energy is the correct approach, is the varying constant is the correct approach. And to me, I think both approaches are not correct. Eventually, these things are there to explain any physical theory is valid only to the extent it can explain something. Beyond that, it is still speculative only. For example, Newton's law is perfectly fine into day-to-day observations, and we don't have to worry about general relativity to be applied. But when we are talking about GPS systems and the correction to the GPS satellites, then we do need the knowledge of the general relativity. And because very small effects can propagate over time and create problems. So I think none of the models can be really seen to be good forever. Is that, have I replied the question, or I diverge from the question somewhat?
No, this is okay. There's another question here: is how will affect the cosmic background? It will have some effect on the cosmic background in some.
Yes. Cosmic microwave background, yes, this is very important thing we want to study, and we have only studied it of first peak, location of the first peak, which is very easy to do. Otherwise, CMB analysis itself is very involved. It requires very detailed calculation, a very time-consuming calculation, and we are working on it. At this moment, we can only say that our indication is that it will fit the data well based on the first peak and based on the information it has provided that the baryonic matter is the same in the CCC plus TL model as in the lambda CDM model, and the BAO data, baryonic acoustic oscillation data, is also compliant with the lambda CDM. So we are very hopeful it will be fit that and will provide some additional information.
Wow, amazing. And finally, Dr. Gupta, we have the last question is, with lambda CDM, total energy keeps growing like volume. How is this with the CCC plus TL model?
Yeah, actually, the energy, because the universe is expanding and we have additional, what is causing the expansion when the gravitational pull is there, why there is accelerated expansion, it should be retarded expansion if there is expansion at all. So if we have found, which I have not discussed in the table I gave you, the Q0, which is the deceleration parameter, which we call, or acceleration parameter, you might say, is higher, in fact, than that in the lambda CDM model. So yes, alpha is, or variation of physical constant, are causing the acceleration and has the effect similar to that of the cosmological constant.
Thank you, Professor Gupta. Well, it's been a delightful lecture of yours, and we have enjoyed every moment. And we appreciate a lot your time and dedication for this fundamental knowledge that you are studying. Thank you very much for your lecture.
Thank you very much indeed for inviting me to lecture. I hope I have supplied the information which was needed, and I encourage any of the participants in this, any of the attendees of this lecture, virtually or in person, if they have any questions, they can always ask me the question, and my email address is given right at the bottom here. Write to me, I'll be delighted to answer. Or if I can't answer, then maybe that will be good, because then I have to look into it. That might be something to learn from you.
Right. Okay. That's a good thing to you are taking it a good way. This question.
Actually, for me, every question people ask is a learning experience. This is why I wrote in my about me that when I teach, I learn from students. Teaching is a learning experience. Similarly, when I give a talk, people ask questions. those questions which I answer, they are easy. Which I can't answer, then I learn something from those. A lot more. Thank you again. Thank you. Thank you.
Thank you, Professor.
Thank you. Bye-bye now.
Bye-bye now. Thank you very much.
Can I close now? Can I close?
Yes.
Thank you. Thank you. We'll be in contact. Bye-bye.
Thank you, Professor.
Thank you.